you to wait until you see my message in the chat.
Sure. Hello, I'm Min-Young Kim. It's a pleasure to welcome everybody to the number theory section of the virtual ICM 2022. The speaker for this session will be Philipp Habegger from the University of Basel, and he'll be speaking about the number of rational points on a curve of genus at least 2. Over to you, Philipp.
Thank you, Min-Young. Thank you for the introduction, and honored to speak here at the virtual ICM in 2022, number theory section. So I want to start by posing like a general problem that concerns Diophantine geometry or Diophantine equations. So what can we say about the set of rational solutions, so x, y here, of bivariate polynomials? So I've given 3 examples here. First one, quadratic polynomial, which describes the unit circle. The second one, a cubic one, and the third one of degree 5, which you may recognize in connection with Fermat's last theorem. So in algebraic geometry or Diophantine geometry, it's often useful to not work with affine equations, but with homogeneous equations that define projective curves. And so I will be secretly doing this as is displayed here. So we have now polynomial equations in 3 unknowns with homogeneous of degree 2, 3, and 5 respectively. In all 3 cases, we get a smooth projective curve in the projective plane. So if you look at the complex solutions of these equations as points in the projective plane, what you'll end up with is with a compact Riemann surface. And topologically speaking, we have 3 categories that will play a role later on. So we can look at those curves of genus 0, and topologically speaking, they correspond to the sphere here, and the first equation leads to a curve of this type. The second class would be in genus 1. So topologically speaking, we have a torus, and the second equation falls into this category. And then all higher genus curve, so genus beyond 2 and higher. And this curve here has genus 6, so it falls into this third category. So topologically speaking, this one here looks like a compact Riemann surface with 6 holes in them. So you can also think of these 3 columns as characterized by the sign of the Euler characteristic, which would be positive, or on the left, it would be 0 in the middle, and it would be negative on the right. So it turns out that this characterization of smooth projective curves also has something to say about the set of solutions of the corresponding Diophantine equation that we have on top there. So let's see what happens in low genus, in genus 0 and 1. So we saw before genus 0 is, for example, presented by this equation here, which looks like a circle. And well, if we look at the C points, then we get a sphere. And well, it's a classical fact here that as soon as you have a single rational solution to an equation like this, then the curve, the projective model of the curve becomes isomorphic to the projective line over Q. And therefore, the set of rational points of the curve is in bijection with the set of rational points of the projective line, and therefore in particular infinite. So there are 2 cases here. Either we have no rational points or we have infinitely many. That's what can happen in genus 0. So in genus 1, where we had this cubic example before, topologically speaking, the projective model would look like a torus. There are also 2 things that can happen. Either we have no rational points at all, or we have a rational point. And here, if you look at the projective model I had before, there is a rational point at infinity. Once given this point, you can upgrade the set of points here. You can upgrade the structure to an algebraic group. So this will become an elliptic curve as soon as you have the this equation together with the marked point. So we get a group structure, looks like the one coming from the torus. Now the important input from arithmetic is the theorem of Mordell-Weil, which says, well, in the classical, the first version was due to Mordell for curves over the rationals, later generalized by Vey to higher dimension and number fields. So if we have a curve of genus 1 together with the marked point, then we get an abelian group. And the arithmetic feature here is that this is a finitely generated abelian group. So this is what the main part of the theorem says. So typically speaking, this is on the right here, we have this blue curve that would correspond to real solutions of a certain elliptic curve, and I'm doubling the point P here. This is the classic construction. We take the tangent at the curve through P, and then take the mirror image with respect to the x-axis, and that would be 2 times P. And adding 2 points, which just corresponds to taking the line through P, these 2 points. So that's how you get the group law, and the theorem says that this is a finitely generated. So also here we have 2 cases, either no points, or there is a point, and in which case we get a finitely generated group. In a sense, this is the set of solutions is sparser than in the genus 0 case, in a way that one can make it precise. So what happens in genus beyond 2? And this is a Mordell conjecture proved by Gerhard Faltings in 1983 that says, well, in genus at least 2, if your curve is defined over Q, or more generally over a finite extension of Q, a number field, then the set of solutions is finite. So C of K is a finite set. That's the conclusion of the theory. So after Faltings' proof, there was a different proof by Paul Voida in the early 1990s, which saw a lot of developments, for example, simplification by Bombieri, and various quantitative versions that I'll talk a bit about later on, and also higher dimensional versions for subvarieties of abelian varieties. So any curve of genus at least 2 can be embedded into its Jacobian, an abelian variety of dimension G, if given a base point. And the method here works for subvarieties of abelian varieties. And in general, that was developed by Faltings, Hindley, Habegger, also in the 1990s. Let me also point out that there's a recent new proof of the Mordell conjecture, and also goes beyond, by Lawrence and Venkatesh from 2018. So if you're outside the realm of abelian varieties for a general projective variety of any possible dimension over number fields, beyond dimension 1, little is known in general. But there's a conjecture by Lang that expects that the set of K rational points is not Zariski dense if the smooth projective varieties of general type. And so general type is the higher dimensional analog of genus at least 2. So in dimension beyond 2, not much is known in general. So I'll stick to the dimension 1 case for the remainder of the talk. Okay, so let's suppose we have a genus G curve, G is at least 2, and the curve is presented as a 0 set of some collection of polynomials in some projective space, and the coefficients are in the number field. For example, you can also just take K equals Q here if you'd like. So 2 fundamental questions that we could ask is there an algorithm to produce all finitely many points, the projective coordinates of all finitely many points? And so this is wide open question. So we don't know of any algorithm that can do this in general. And the second question is, well, maybe a bit more modest. Can we at least produce an upper bound for the number of K rational points? So given invariance or the complete data on C and K. So the second question, there's more to report on in general. In fact, already after Faltings' proof, Parthen, he gave a way to extract an upper bound from various invariants that are attached to the curve that come out of Faltings' approach, and that was written up in a paper by Spiro. Then later, when Voida introduced his second proof of the Mordell conjecture, he also gave in principle an upper bound that can be computed, and things were made explicit, and well, in the end, it's completely explicit in the 1990s and early 2000s, to work by Bombieri, Diego, and others. And then the culmination was the result of David Philipp and Raymond, the early 2000s, who gave a completely explicit upper bound for the number of K points in terms of various invariants of the curve and also the Jacobian of the curves. So I'm not going to write down the explicit version, but there is one. You can ask yourself, what kind of invariance do we need to get an upper bound for the number of K points? So if you look at this genus 1010 curve given by y squared equals this polynomial in degree 2022, well, there's a suitable projective model that makes this a genus 1010 curve. And as you can see, there are at least 2024 rational points just by plugging in the integers between 1 and 2022, y equals 0. And the point at infinity, there are 2 points at infinity in this particular case. So we get at least this many points. And this simple-minded example can be made more sophisticated. And Mestre, he has, I think, the best general lower bound. So he shows that in all genera, at least 2, there is a curve over Q that has at least 8G plus 16 rational points. So a factor 4, but better than what this approach here gives. So in any kind of upper bound for the number of rational points, you need to include the genus in one form or another. Let me move on. Okay, so one particular feature about curves, algebraic curves, is that they arise in families. So I've here presented again an equation of the type y squared equals a polynomial in x, but here S will be a varying parameter, and the curve here, or this equation represents a curve in genus 2, and I'm allowed to vary the parameter over all numbers not equal to 0, 1, 2, or 3. For simplicity, I'm just looking at integers at this point. And that's, well, to make sure that this right-hand side here is square-free and that we actually get a curve that has no singularities. Just looking at smooth curves here. So, and then we get one free point here, namely the point where the x-coordinate is S and the y-coordinate is 0. And as you see, as you let S vary, this point gets larger and larger in value less. So the question is, this set is always known to be finite by Faltings' theorem. Can we get in a good upper bound for this cardinality in terms of S? Now, so the genus here is fixed, and the number field Q is also fixed. And a special case of the powerful Caporazzo-Harris-Mazur uniformity conjecture predicts that the number of rational points here is bounded from above uniformly as S varies over the parameters I'm allowing here. So we're very far from knowing this, having a proof of this, and some evidence is given that by Poggi in 2018, which showed that on average in genus 2, the number of rational points should be bounded. And well, furthermore, the conjecture here, the uniformity conjecture, follows from Lang's conjecture on rational points in higher dimensional varieties that I talked about just a few minutes ago. So we're far from getting uniformity, but we can still ask how good can we, what kind of upper bound can we get in terms of S as S runs over the integers that are allowed here. So now we come to some important gadgets that we need in this field, the height functions. And they were used in both approaches to the Mordell conjecture by Voida and Faltings. And so the height of a rational number is very easy to understand and write down. So we just take a rational number x here for simplicity. It's p over q, where p and q are co-prime integers. Q is non-zero. The height of x is just, we take the maximum of the numerator and denominator of x. That's all there is to it. And then for normalization purposes, we take the log. So it's about the number of bits a computer would require to save the information encoded by the rational number x. That's if we take the log. So rational numbers are one thing, but we can also work with points on projective space. So we have this point P here on projective n space. Any point that's rational can be represented by a tuple of n+1 integers that are co-prime. Right? So this tuple will be unique up to sign. And if I take the L infinity norm, just the maximum of the coordinates, that will be uniquely determined by P because of kill off all common divisors. And then again, it takes the log whole thing. And that will give us the height of a point on a rational point on projective space. So one feature that this height has in this rational setting is that if I look at a ball of a certain radius here, B, of rational points of height at most B, then I'll get a finite set. And it's quite straightforward to see, because if I'm bounding this expression from above by B, that just amounts to bounding the coordinates here by e to the b, and because they're integers, there's a finite many possibilities. So this is a balls of finite radius of bounded height if we're looking at rational numbers, and that's one way to prove that the Diophantine equation has finitely many solutions just by showing that they're solutions of bounded height, which is, of course, then the main difficulty. So there's also a way to define the height of an algebraic number. It extends to q bar, and for example, the height of square root of 2 is log of square root of 2. Then this finiteness statement that I said, it doesn't hold in general anymore, but it holds if you're over, for example, if you look at points over a fixed number of fields. So the height extends to algebraic points, and it also extends to algebraic points of projective space. Okay, but we were talking about elliptic curves before, and also Jacobians of curves. So there's a group structure involved in both cases, and let's see how this height interacts with the group structure. So I've given here an elliptic curve, y squared equals x times x minus 1 times x minus 11. And this is a point, a rational point, even with integral coordinates on this curve. And we can ask ourselves, how does the height behave if I start multiplying the point by an integer k? And that's what we have plotted here on the right. So the x-axis here would be k, and the y-axis will be the height of h, the height of k times p. And this is, if you squint your eyes, you'll recognize this is just it's quadratic growth. And the leading term in front of k square has a significance. Namely, if I take the height of k times p and normalize it by dividing by k squared, then in the limit for k goes to infinity, I'll get a real number. So the limit exists, and it's what is called the canonical or Néron-Tate height of the point p. And this works for all algebraic points for all points on elliptic curves. And so this height has nice properties that are compatible with the elliptic curve. So this is no longer just a height on projective space, but it's a height attuned to the elliptic curve itself. For example, if I multiply a point by k, then I'm multiplying the Néron-Tate height by k squared. Just because you plug in here a multiple, then I'm shifting the sequence by factoring k squared. In fact, this generalizes to the following, namely that the Néron-Tate height actually even extends to a quadratic form on the algebraic points of the elliptic curve tensor to R. So what gets lost in this passage is that, well, the torsion points are precisely those points of height 0. And of course, they get lost by tensoring with R, but we get a quadratic form here. And that means, in a sense, we'll be able to do Euclidean geometry in this real vector space here, or at least finite dimensional subvector spaces. Allow us to do Euclidean geometry. So that's how heights can be made to interact nicely with elliptic curves and more generally Abelian varieties. So I already spoke about families of curves, and in fact, elliptic curves also arise in families. So here's an example. A classical example is the Legendre family of elliptic curves, which is parametrized by this number lambda here, which is allowed to take any value of the projective line except 0, 1, and infinity. So again, I'm excluding 0 and 1 to make sure that this right here side here is square free. And so this is what the picture could look like. Down here we have the projective line minus the 3 points, and so this could be 0 and 1, so they're missing. And at the top of any point, we have an elliptic curve. So topologically speaking, they're all tori, so they look the same, but they have a different complex structure, and that's why I colored them differently here. So there's something moving that goes beyond the complex structure is moving on this family. So in this family you can think of it as a surface, because we've got a one-dimensional base, and each fiber is one-dimensional. And so inside this surface, we can consider a curve. Let's look at this curve here that I've plotted with this purple squiggly lines. And for example, you can take the curve here, where just the x coordinate happens to be fixed to be equal to 2. And for the y coordinate, we have 2 possibilities, and there's some ramification. So this is a curve inside this family of elliptic curves, and it's somehow horizontal inside. Now on this curve, we have 2 heights now, right? We have the height of lambda, which, if, for example, lambda is a rational number, I explained what the height was before. And we also have the height in the vertical direction, the Néron-Tate height on the fiber. Now, the Néron-Tate height function is varying across this family. So this is not going to be constant here, as I let lambda vary in general. And in fact, I create a plot here on the lower right. You'll see black dots. And the black dots, the x-coordinate corresponds to the height of lambda, running from up to log 256. And the y-coordinate corresponds to the Néron-Tate height of the point above, well, either of the points are both at the same height. And as you can see, the height here, the black dots, they kind of cluster around this red line. And this red line, right here are some coordinates are missing. This would be 1, 2, and 3. The red line has slope 1.5. All right. Sorry, I think it's 2/3 here in this case. This one. So as you can see, that the black dots, they kind of approach this, well, they stay close to this red line. And so you can ask yourself, the two coordinates are related, and how exactly are they related? The suggestion is that the quotient, the ratio should converge to something as the height of lambda goes to infinity. So in fact, this is a theorem by Silverman in the 1980s. We show the following. So if we have this is a more general setting. Now we have a family of abelian varieties here. Over a one-dimensional base. The base is again a curve as before, but each fiber is now an abelian variety of some fixed dimension. The thing varies algebraically. And we can fix suitable height functions by choosing embeddings, for example, of the base into projective space. And there's also a way to choose a suitable Néron-Tate height fiber-wise from this family of abelian varieties. So Silverman's theorem says the following. So we have the family, and we need some kind of curve inside it, and that's represented by a section of the base here, which is a slightly different setup than before, but it's morally the same thing. So we have the section that maps a point on the base to the family, and now we want to compare the Néron-Tate height that the section attains at some lambda. And the theorem is exactly that the ratio exists as I take the limit of on the base. The height goes to infinity. So the ratio will exist, and it will equal to some other height, which has an arithmetic meaning. So what is this limit value here? Okay, so we have this family of abelian varieties over a one-dimensional base. And this one-dimensional base is a generic point, and above the generic point, we get an abelian variety over the function field of the base. And on this abelian variety, we can also introduce Néron-Tate height. And that will be the Néron-Tate height h hat. Eta here represents the generic point on the base, and this represents the Néron-Tate height on the generic fiber of this family. So the limit here exists and equals to this the height of the section here on the generic fiber. You can think of the section as a point on the generic fiber. So the nice feature about this theorem is that the limit has an arithmetic meaning, because we already know that the Néron-Tate height is 0 if the point is torsion, if and only if for the case of elliptic curves over number fields that we've seen before. One direction of this implication holds in general, namely that if this point here coming from the section is of finite order, then the Néron-Tate height is 0. And the converse also holds. So we get an if and only if statement if the generic fiber has trivial geometric trace. So there's that essentially means that the family of abelian varieties is moving in a certain sense, in a certain maximal sense. So in these cases, we can say when is this height here positive and when it is 0, just depending on the arithmetic of this section. And if it is positive, well, then we have the following conclusion, namely that if the section happens to specialize to point of finite order, then this will be 0 here. But if the limit is to something positive, that means those points for which the section specializes to something torsion the parameter has to have bounded height. That's one conclusion of this theorem, if we know that this value here is positive. So we get a boundedness of height statement for parameters where the section attains a torsion value. And that's important because, as we saw before, bounding the height sometimes leads to finiteness statements. Well, it always does if we're over a number field, but it's an important piece of information. So one application of this theorem of Silverman towards unlikely intersections, which was the topic that saw a lot of development in the last 15 years, due to Masser and Zanier. So what they look at is they have a curve here inside the fibered square of the Legendre family. So this is now a three-dimensional variety. And under the hypothesis that the curve is not contained generically in a proper algebraic subgroup, they show that it contains at most finitely many points. So now these points are points on the same Legendre elliptic curve that are simultaneously torsion. This is kind of fits into this unlikely intersections framework because we're imposing two restrictions on the point, namely that both coordinates have finite order. And well, this falls, as I said, in this framework of unlikely intersections, and this is a special case of a conjecture of Richard Pink, and the result here was generalized by Masser-Zanier and Courville and Masser-Zanier further in the last 10 years. So the proof kind of works as follows: if they're both torsion here, then on the base, the parameter has bounded height by Silverman's theorem. And then the second input, going from boundedness of heights to fineness, requires what is nowadays sometimes called the Pila-Zanier counting strategy, which led to a lot of development also in other areas of Diophantine geometry, around the André-Oort conjecture, for example. So this is an early implementation of this Pila-Zanier counting strategy that uses right. So I want to go a bit higher dimensional now, and so instead of looking at the fibered square, I'm looking at a fibered power of the Legendre family of elliptic curves. So ETG is the G-fold fiber power of the Legendre family that we had before. Now a point in this family here would correspond to G points, each on the same Legendre elliptic curve. And because I have a height on each curve, I can just take their sum and get a reasonable notion for height on this family of powers of elliptic curves. So in an attempt to somehow study the higher dimensional analog of Silverman's theorem, led to the following height inequality. So now X is a subvariety of EG of any possible dimension. I'm going to assume that it's not trapped in a fiber, so it dominates the base over Y2. And then there's also a condition here on what happens on the generic fiber. So on the generic fiber, X is not allowed to be essentially a union of components of algebraic subgroups. So this corresponds to, in Silverman's theorem, that this Néron-Tate height is positive, right? So under that condition, we had a bound on points on the base where the section attains torsion value. So in this setting, what we get is a height inequality between a height on the base and the Néron-Tate height, which lives on the fiber. So the theorem says the following: so the height on the base is bounded from above linearly in terms of the Néron-Tate height on the fiber, and this 1 plus 1 is because we don't say anything about points of small height, Néron-Tate height. So this holds not for all points on X, unfortunately, but you have to exclude well, Zariski closed proper subset of X. So some positive codimension subset of X where this inequality can hold because there's some algebraic group interactions going on there. So the height inequality has the following conclusion or application that goes also in the direction of the previous slide, namely that if the hypothesis is satisfied and if P happens to be in general enough position so that the inequality holds, and if it happens to be a point of finite order, then this will disappear, and we'll just get that the height is bounded by some constant, right? So we get a bound for the height on the base for torsion points in the fiber, and that is one way to approach certain unlikely intersection type problems in these families of Abelian varieties. So this is for the family of Legendre elliptic curve, or powers of the Legendre elliptic curve over a one-dimensional base. And so more recently, together with my co-author Ziyang Gao, we extended this result, this height bound, to families of Abelian varieties over a general one-dimensional base. So Abelian variety of not necessarily of this structure, but any Abelian variety of a curve. family of abelian varieties over a curve. So we have to be a bit more careful there because of the trace could be 0, which is not the case here, but it's in this spirit. So after that, we were interested in what happens in higher dimensional bases over higher dimensional bases of families of abelian varieties, and I'd like to motivate the reason why this is has interesting applications by following slide. So if we go back to our original question on rational points on curves of genus at least 2, then, well, all these curves, if the genus is fixed, any curve will arise as a fiber in some universal family of curves of genus G. At least if you introduce suitable level structure, then you can realize your curve C as contained in some large family of curves that lies over this moduli space of curves, which is everything here is quasi-projective. And this large moduli space of curve, it's itself a variety of dimension 3g minus 3. I have it here down on the bottom. So, and this is always greater than 1 for g at least 2. So connecting curves to abelian varieties is you take a curve and you attach to the curve its Jacobian. So in this diagram, that corresponds to taking a point here and attaching the point to its point in AG. And what is AG? So this is the moduli space of g-dimensional principally polarized abelian varieties with the level structure compatible with the curve. And on top of that, we have a universal family of these abelian varieties. So we get a map from MG to AG. This is a morphism. And we would like to have some way to get from left to right here on top. And what we do is look at what is sometimes called the Faltings Chang map. So we take a tuple of points here on a fibered power of this universal family of curves. So we have n+1 coordinates here, and each point P1, P0 to Pn is on the same curve. And what we can do is we can look at successive differences of these points. And we can consider these differences as points on the Jacobian, because we can think of them as, we can map them through to their degree 0 class, pick 0. So this gives us a morphism from the fibered m+1-fold fibered power of this universal family of curves to the m-fold fibered power of the universal family of abelian varieties, base change to n. So this is just a morphism of varieties, and let's see how this morphism can help. So for this particular morphism, we get a similar height inequality. This is now together with Veselin Dimitrov, Xiang Gao, myself from 2021. We get a height inequality as follows. So this parameter m I had on the previous slide, we have to fix it, we have to settle down on a value, and it turns out you can do anything, take any value of m that's greater than 3g minus 3, which is the dimension of mv. Then for any point, any m+1 tuple of points here on in this fiber power, this corresponds to m+1 points on the same curve. We can look at their differences. So then we will be on abelian varieties here of Jacobians of the curve, and then fixing suitable Néron-Tate heights on everything, and also a suitable height on the bases. We get this height inequality here. So the height on the base is bounded from above linearly in terms of the Néron-Tate height on the coordinates upstairs. And again, the caveat is that this holds outside as a risky closed proper subset of all points here in this fibered power. So there's some exceptional subsets that in practice we handle using an induction on the dimension type argument. So several things go into the proof of this theorem, namely techniques of height theory, but we also need somehow an analog of this non-vanishing of the Néron-Tate height of the generic fiber that appeared in Silverman's original version. So this kind of condition has an analog here that has to be verified in this setting. And writing down the analog is more sophisticated than just looking at the Néron-Tate height on the generic fiber, and it requires, for example, the machinery of Betti coordinates, which was, I think, probably first used Marciarizani in the context of Diophantine geometry, and the result I mentioned a few slides before, and then later studied by myself. André Corvaille-Zanier did a systematic study, and in 2018. And for our work, we need deep work of Gao on the mixed X general theorem for this universal family of abelian varieties to get to make sure that the analog of this condition here is satisfied in the context that we're interested in here. And so this mixed X general theorem by Gao it's in this family of functional transcendence results that have played a big role also in the André-York conjecture in the last 10 years. So in the context of Shimura varieties, such functional transcendence results were established by Bakker, Klinger, Mach, Pila, Zimmerman, Ilmo, and Yafai, and Zimmerman's ICM talk in 2018 covers some results in that case, in the EAG case. And here we're using something, the family, the universal family of abelian varieties, and that's why it's sometimes called the mixed case. Right. Okay, let me move on. I'm going to next one. There we go. So the motivation was to say something about rational points on curves. And so the application of the height inequality on the slide before to rational points on curves of genus at least 2 is the following. So this is also together with work with Veselin Dimitrov and Xiang Gao. So the setup is as follows. We have the genus, there's at least 2, working over number fields. And then we get a constant that depends on the number field, or actually it's just a degree of the genus, such that if we have any curve over K of genus G, then the number of K rational points is bounded exponentially in the rank of the Jacobian, the K points of the Jacobian. Recall that this is finite by Moduli. A finite number, and the base here, the constant C here, is allowed to depend on the genus and the degree of the number field K. I'll explain the next slide approximately how to get from the height inequality to this theorem. So this is answered a question by Barry Mazur, and there's also been some recent developments by Lars Kuhne, who made an important contribution by removing the dependency here on the degree of K over Q in this constant, which allowed for some additional uniform results. Yuan gave a new proof of this bound using theorem, a new framework of Arakello's theory developed by himself and Shubo Zhang for quasi-projective varieties. And much earlier, already in 2007, David Philippon gave a bound of the same quality, so something exponential in the rank of the K points of the Jacobian, if everything is inside a power of an elliptic curve, right? So if your curve C is inside e to the g for some elliptic curve E, and the point was that the constant did not depend on the elliptic curve, whereas here it's kind of the same feature, the constant does not depend on the abelian variety of the Jacobian itself. So completely parallel to these developments, there's also important work by various authors. Let me just include Jennifer Bauer-Kishma, Dogra, Richthofen, Katz, Min-Young Kim, Müller, Rabinoff, Stoll, Teutmann, Zurich, Brown, and others who use the Jaboty-Coleman method and its extension, quadratic methods, to get very clean upper bounds for the number of rational points under the Jaboty-Coleman restriction on the rank of the modality group. So that gives clean upper bounds that are sometimes good enough to actually say something about the set of K rational points. Whereas here in our results, the constant you see here is, we're still not able to compute it. And I guess if we were, it would be astronomically large in order and not be able to say something about the actual set of K rational points. Okay, let me say something about how to get from this height inequality, I had this few slides before, to the number of rational points. And so the situation given by us by Voida's method, so let me start out with the basic setup. So the curve is contained, let's assume that it's already embedded into its Jacobian. So we've already fixed the base point. We used embedding with the curve in the Jacobian, and the Jacobian itself, or the curve, corresponds to some point S on the moduli space of curves, and gamma here is just the set of the group of k-rational points on the Jacobian, which is a finitely generated. Now, the theory of heights, as I said before, allows us to think of gamma tensored R as, well, it looks as an Euclidean space, because at least the square root of the height will become an Euclidean norm. Now, Voigt's method and the extensions by various people, the 1990s and early 2000s, like Bombieri de Diego, Raymond, they're able to show that. So if we're interested in the points on the curve that are rational of sufficiently large height, then their number is bounded already quite uniformly by, for example, this bound by 7 to the rank of gamma. And so what does large mean? Large means that, well, we're outside this blue radius here. And more precisely, if the height, the Néron-Tate height has to be large, has to be larger than some constant times the height of S plus 1. So that's what it means to be large, and C big is some large constant, just depends on the genus. So this is what Voigt's method together with called Mumford inequality gives you. So to bound the number of rational points, you need to say something about those points of small height. So those points where the Néron-Tate height is less than R squared. So here I've this this green circle corresponds to the circle of radius R here. And so our height inequality essentially tells us that if I'm looking at these differences, then typically these differences are at least mR squared, where R squared is some smaller proportion of H of S. So these corresponds to these blue circles here, lowercase r. Right. So what, and this 3g minus 2, that was just the constant m in the theorem above, one choice of the constant m. And so what it tells us is that, well, at least generically speaking, the number of points that can fall into one of these blue circles here is bounded from above by essentially 3g minus some constant depending only on g. So it's kind of like a social distancing principle. We can't have too many points inside one of these blue circles. Now, the number of blue circles that you need to cover this large, or blue disks that you need to cover this large green disk is just given by the ratio of the radii to the exponent equal to the dimension of the ambient space. That would be capital R divided by lowercase r to the rank of gamma, right? And so you see here by the value, by the choice of these, or the possible choice of these the radii here, the dependency on the height of S here cancels out in taking the quotient. And so the quotient will just be the ratio of these two constants to some exponent, and these two constants just depend on the genus and the various choices of height functions that one did at the beginning of the proof, but not on the actual moduli of the point S itself. Okay, so that's how this height inequality comes into the picture in the proof. And so let me, on my last slide, let me come back to the original curve I had at the beginning, or a family of curves, this family of genus 2 curves here, y squared equals something of degree 5 in x, where the parameter s is allowed to take integer values except 0, 1, 2, and 3. And here it's presented on the right. Now, if you want to get an upper bound out of the theorem, well, you need to know something about how the rank here develops, or how it grows, or how it can be bounded as S varies. So as we know, it's very difficult to actually compute the Mordell-V rank in general. So there's no known algorithm that always works at the moment, but you can get an upper bound for the rank. That's good enough for these, give an application that as follows. So the rank of the Jacobian, the Q points of the Jacobian of the curve CS, and this is in the book by Silverman on Diophantine geometry, the rank is bounded by 2 times the number of distinct prime divisors of this expression, S times S minus 1 times S minus 2 times S minus 3. And this grows like log S over log S as S goes to infinity. And that gives an upper bound for the number of Q points, which grows like O of S over 1 over log S. So this is smaller than O of S to the epsilon for every positive epsilon. So we get a statement here that on the number of points that doesn't depend on the theory of Jacobians, but gives us slow growth. So thank you for your attention.
Well, thank you, Philip, for a beautiful talk about a beautiful set of results. Unfortunately, we don't have time for questions, but if you put questions for Philip on the Discord server, then he'll answer them after the end of this talk. Thank you, everyone, for coming to the number theory session of the virtual ICM 2022.
Thank you.
Bye.
Bye-bye.